Hey guys, welcome to the second video in the Simply AI series. Today, we'll be looking at getting started with AI. We will look at understanding the history of AI, machines and thinking, prominent fields of AI with the machine learning introduction, and classification and regression. I hope you enjoy. Now, why is it important to learn the history of AI? Well, history gives us a deeper understanding on how and why certain aspects of AI came into being and hopefully will guide us on how to explore them in the future. Additionally, history helps us to avoid mistakes that lead to big failures. The orange block here pertains to general AI and the green blocks pertain to deep learning. The Turing test tried to address one of the main premises behind AI in the 1950s. Can machines think? How do you think that was addressed? Well, like all smart engineers, it was avoided and replaced with something simpler. Later, we will see exactly how that was addressed. The 3 Laws of Robotics by science fiction author Isaac Asimov were also proposed in the 1950s. John McCarthy, one of AI's founders and a pioneer in mathematical logic, coined the term artificial intelligence in 1956. In 1965, Gordon Moore, the co-founder of Fairchild and Intel, predicted that the number of transistors per silicon chip would double every year. Moore's law is a violation of Murphy's law, which is that anything that can go wrong will go wrong. 1974 to 1981 was the period of the first AI winter, where everything AI took a big hit. This was the result of 4 big AI setbacks: the 1966 failure to automatically translate Russian documents, the 1969 hype around neural network perceptrons failing to deliver, the 1973 Lighthill report in the UK discrediting AI as only solving toy problems, and deep funding cuts by DARPA in the 1970s. Some work on neural network backpropagation and expert systems continued, nevertheless. In the early 1980s, expert systems became popular and led to another round of AI hype. But the promise of a general-purpose expert system never materialized, leading to a second AI winter during the period of 1985 to 1990. In the 1980s, Japan's huge investment of $850 million into fifth-generation computer projects also failed miserably. AI winters were due to excessive hype, exaggerated promises from technology companies looking for funding, and huge promotions in the media resulting in wild, unfulfilled expectations of end users. But more importantly, this was also because people chased one promising AI field and tried to sell it as a cure for everything. AI has always been historically an elusive technology that was easily marketable but very hard to deliver. The late breakthroughs in hardware, especially leveraging the GPU hardware, made using neural networks feasible and led to a boom in deep learning since 1999. Replacing complex AI algorithms by a simple, smart approach is the key to this success. Let super-fast machines automatically figure out patterns from large amounts of data. The internet and smartphones provided access to large amounts of data, and a relatively cheap GPU hardware allowed super-fast computations. So the question becomes, if historically AI had so many failures, is it still worthwhile to explore all of the other areas instead of sticking with deep learning that seems to be working so great for so many applications? It would be great to comfortably ride the deep learning train everywhere. However, if the only tool you have is a hammer, you will start treating all your problems like a nail. If we look at how humans operate, we don't need millions of labeled pictures of something before we can start to recognize it. To reach a higher level of intelligence, like all problems, you need to understand the nuances of different problems and use the right techniques to tackle them. And understanding what to use, when to use it, and how to leverage this knowledge for pragmatic, real-world applications is precisely our goal here. So let's go beyond the hype and uncover what really is AI. First, let's tackle a fundamental question. Can machines really think? That was a hotly debated concept since the very early days of computing. In 1950, Alan Turing published the Turing test to address this very issue. Here's how the test works. Computer A and human B can only communicate with human operator C via a simple interface such as text. Operator C asks questions to computer A and human B, and then, based on their responses, C judges whether A and B are human. Computer A is considered artificially intelligent if the human operator C cannot reliably distinguish A from B. If you think about it, the test effectively changed "can machines think" to "can machines do what we, as thinking entities, can do?" This has been the go-to test as a proof of intelligence. Chatbots passed the Turing test in 2014. So can you say chatbots think? And effectively, can chatbots replace a thinking human? Well, obviously not always. In 1980, John Searle came up with the Chinese room counterargument. If computer A has a huge lookup table that has answers to all questions, and computer A merely responds by mapping questions to the lookup tables, can A be considered artificially intelligent? Is Google Home or Apple Siri intelligent? So, although these tests can rule out obvious non-intelligent behaviors, being artificially intelligent or being able to think is complex and not universally general. You always evaluate intelligence in some context or for a sample problem, as AI Winters taught us that general intelligence remains elusive. Now, we will briefly look at the many prominent fields of artificial intelligence and get an idea of things known to be possible in AI today. After that, we will go in depth into some of these fields to understand how they work and look at some sample applications that use these fields. Take a look at this picture for a minute as it's quite busy. AI is indeed quite huge, and it took me a while to fully complete this picture. Each box here represents a field of AI. Some of these boxes can expand to a tree under them, each with its own unique set of techniques and algorithms. Let's first start with machine learning. So, what is machine learning? Very briefly, it is learning that is not procedural but from data. Instead of a system using a complex procedure for detecting, say, a cat, the system learns from sample data, identifies patterns, and makes decisions. Let us take an example on how you identify if an object is a study table. To declare something as a study table, you first need to be able to unambiguously define it. So let's define a study table. A piece of furniture typically having a flat top where someone can sit and perform tasks such as writing, reading, or using a computer. With that definition, let us come up with an algorithm that can identify if an object is a study table. You need an algorithm with logic that understands unique characteristics of a study table and uses such characteristics to distinguish a study table from other objects. Let us see how such an algorithm would look like. First, you see if the object in front of you is big enough. Most study tables are around 3 to 5 feet in width and about 3 to 4 feet high. Why do we do so? Because an object like a tiny watch cannot be a study table. Next, we would probably see if it has a flat surface at the top. Then, we would see if it has legs or some structure that supports the flat top surface. At this point, there's a high likelihood of the object being some sort of a table. Then, you would look for some fine structural features or identify additional things sitting on top of the table to distinguish between a study table and, say, a dining table. A keyboard stand attached under the table will allow you to declare that this table is indeed a study table. A computer monitor or a table lamp on top of the table will also increase the probability of the table being a study table. A bunch of books, a stack of papers, a pen holder, or a pen or pencil on top of the table will also increase the probability of the table being a study table. Someone sitting at the table reading a book, writing, or working on a computer will conclude the table to be a study table. So to reliably detect an object as a study table, we will have to write an algorithm which performs each of these steps in the same order as we listed here. Such an algorithm may require additional algorithms to perform the smaller steps. For example, in step 2, we stated that we should identify if the object has a flat surface on top. How does a machine figure this out? This requires yet another algorithm. Look at the area near the top of the table and detect all edges and corners. If there's an edge that forms a closed shape that spreads across the entire width of the table, the object has a top surface. If there are additional edges that do not form closed shapes, there's a high probability of the top surface to be a uniform surface. As you see, each small step can in turn require additional algorithms whose logic needs to be manually developed. Moreover, the results may be probabilistic in nature. Additionally, there are more issues that we may have to encounter. A dining table that has a structure and design with artistic engravings would be identified by humans immediately as a dining table. However, if someone has temporarily put a computer, books, or pen holders, our algorithm may classify it as a study table, as our algorithm is not rich enough to understand the nuances of dining table structures and artistic engravings. So it is quite hard to truly come up with an algorithm that can identify a study table with 100% confidence and distinguish it from other real-world flat surfaces or tables. Instead of the logic-based approach, machine learning uses a totally different approach. Let us see what a typical machine learning-based algorithm looks like. First, you collect pictures of many study tables along with other similar-sized objects. When I say many pictures, I mean millions of pictures. The more, the better. Next, you label each picture whether it's a study table or not. You split them into two sets. One is a training set to contain 80% of the pictures, and another is a validation set to contain another 20% of the pictures. Show the training set pictures to a system running a machine learning classifier one by one, and also tell it if each picture is a study table or not. The algorithm tells patterns from these pictures. Show the validation set pictures and see how accurately it can detect the pictures. Repeat the above two steps until the accuracy for validation set becomes acceptable. Now, show any random picture and the system should be able to say whether it is a study table. As you can see here, no one designated an algorithm with logic that understands characteristics of a study table like the top surface, support structures, keyboard stand, etc. All you did is collect a very large number of samples with and without the picture of a study table and correctly labeled each of them. The machine learning system did the rest. So how does the machine learning system do this? A machine learning system looked at samples and automatically detected prominent patterns in the data that were present in a study table picture and not in others. Therefore, this is called a statistical approach, as the system automatically uses the stats such that the frequency of a certain pattern present in a study table picture increases likelihood of a study table prediction. Nobody tells the system what patterns to look for or how frequent such patterns need to be for a study table prediction. Machine learning is so cool because it can automatically figure this out. This worked for study tables, but would also work for flowers, cloud patterns, CT scans, fossils, and many other things. In logic, you have a different algorithm to detect different things. Here, you have the same machine learning algorithm that is trained using different training data to detect different things. So you may be wondering, if you did not write any logic, how do you fix the system if it's not classifying correctly? You do that by retraining the system with more data relevant to the problem. If fancy dining tables with books are classified as study tables, you get many pictures in the training set with prominent fancy engravings of dining tables with books and label them as not study tables. The system learns to see that prominent fancy engravings get higher precedence, and tables with such engravings should not be predicted as a study table. Is it really that good? Is there any catch? Actually, it is very good, but as you know, there is always a catch. A machine learning system is as good as its training. If you put garbage in, you will get garbage out. Say you deliberately or accidentally labeled half of a specific type of dining table as a study table. The system won't be able to detect accurately whether this type of dining table is a study table or not. So what qualifies as good training data, and how can we ensure good training? Well, to do that, you need to go a bit deeper, and we'll see that in a later session. Before we go into the details of machine learning, let us first look at two primary uses of machine learning: classification and regression. Now, let's examine what is classification. Given an input sample, a classifier assigns a label to that sample. For example, given a fossil sample, a classifier labels it as from a mammal, dinosaur, or a bird. Such classification is performed using what are called features. The features distinguish one sample from another, as values of these features differentiates one sample from another. Based on these features, input samples form natural groupings which we call classes, and qualify these classes with labels. For example, samples in class bird have similar characteristics such as beak, wings, and samples in class mammal do not have these features. Features are also attributes like a customer's occupation, income, age, transaction history, credit score, etc. that affects the results of a loan application, classified as loan approved or rejected. Thus, Features are characteristics or attributes of an input sample and are typically represented using a vector. In many classification algorithms, this vector is given the name letter X. Labels represent a class of samples and are typically a scalar with name Y for many classification algorithms. There are many techniques of classification. A machine learning-based classifier works as follows. Learning. First, a training dataset trains the classifier. Evaluation. Next, a training dataset evaluates classifier performance using parameters such as accuracy, error, precision, and recall. If the classifier does not perform well, continue learning with more data until performance is satisfactory. Prediction. Provide predictions for queries. Now, let's examine regression. Given an input sample, regression determines a continuous result value. For example, given a fossil sample, determine the age of the fossil. So for an input sample, classification names a class label, whereas regression gives a value. Like classification, regression input comprises features of an input sample, typically represented as a vector named X, and result is a scalar vector, commonly named scalar vector Y in regression algorithms. Some of the techniques that can perform regression include linear regression, decision trees, random forest, k-nearest neighbor, support vector machine, and neural networks. Each such technique has different requirements and performs differently. So what should you use? Well, like many things, that depends on your application. So how does one decide which algorithm to use for their application? There are no set rules for selecting a technique, and it is something that becomes more obvious with some experience. But here is an approach that works under most cases. First, you start with the simplest possible model. For example, start with linear regression and see how it performs. Adjust its parameters to see if it meets desired metrics, like accuracy, error, prediction, recall, etc. Move progressively to more complex models until it achieves required performance. So today, we covered classification and regression here, as machine learning problems typically fall in one of these cases. Classification gives you a binary answer. Does the patient have a disease? Or a multiple choice answer. Is this fossil of a mammal, dinosaur, or a bird? If it's not a choice, regression is used to get a value, like what is the expected sale value of this house? Thus, classification and regression can be used for many real-world applications. In summary, today we looked at the history of AI, machines and thinking, some prominent fields of AI, especially an introduction of machine learning, and classification and regression. Thank you very much for listening to this video on getting started with AI, and I hope you join us for the next video, where we further introduce machine learning. See you then!